Okay. The first of all, so I would like to announce that, yeah, I have really bad cold. So yeah, I'm not feeling very well. But so please understand me. So if today's lecture ends a little bit earlier than usual, okay. But anyway, I will do my best. All right. So last time, yeah, I was in rush. I was in hurry. Then but end the lecture. And anyway, this is the conclusion. So well, if your function is analytic and at some point, well, so I'll say, sorry. If your function is analytic on some disk, well, this is a disk centered at point z0 with radius r0. Then you have the fs of power series representation that looks like this, and whose radius of convergence is r0, and the coefficient there is the n derivative of f evaluated at z0 divided by n factorial. So which has the precisely same expression as we had in the calculus 101. So these are some basic examples of the Taylor series. This is something that we know very well. So this is called the geometric series. And also I will need to add just one more remark on this first part, this Taylor series. This is, well, actually the Maclaurin series. And well, and since this guy, this Taylor series has the center expanded about the origin, and the nearest singularity from the origin is 1, right? So as you can see from here from on the left-hand side, if you plug in z equals to 1, then you can easily notice that you can find a singularity there. So that means, well, from the origin, so your radius of convergence cannot be greater than 1, right? Because, well, because of this reason. So this is the origin, and this is the point where the singularity happens. So therefore, yeah. So this is very natural to say that, well, radius of convergence is 1. However, for the other cases, yeah, so these are some Taylor series of, well, I mean, Maclaurin series of the exponential functions and trig functions and hyperbolic functions. And these, all these formulas, they are exactly the same as the freshman calculus. The only difference is the number here is not a real number, but it is a complex number. And for all these functions, the radius of convergence, the radii of convergence they're all infinities. I mean, so these power series, they converges for all complex numbers. So how do I know that? Because of this formula. So if you cannot trust me, then you try to take the derivative of these functions and evaluate these nth derivative at the origin, then you can easily get these numbers, these formulas. All right, so let me take this for granted. Okay, so now I really want to come back to this part, this guy, because it has a singularity at 1. And the question is, maybe I can try to find not a Maclaurin series, but I can try to find a Taylor series of this guy. Well, instead of Taylor series centered at the origin, maybe I can try to find another center. Say, maybe I can choose my center to be I, the imaginary unit. Then what do you think is the radius of convergence? In that case, if I choose this guy to be my center of the power series, then, well, obviously distance from the center and the singularity is square root of 2. So, well, that means if I choose this guy to be my center of the Taylor series of this function, then my radius of convergence should be not 1, but should be square root of 2. Okay, so let me try to find out if that is really the case or not. So this is the function. And I want to find the Taylor series of this function. about the I. Okay. Well, in this case, for practical computation, so for such an exercise, we never use this formula. So how do I find the Taylor series of this guy at this point? Well, by manipulating this denominator a little bit. So since we are looking for the Taylor series whose center is I, so I need something to do with I for this denominator, right? But you cannot get that number for free. So 1 minus z, and I will need plus I and minus I. Then this is going to be 1 minus, 1 minus I, and parenthesis, minus z minus I 1. Then this is what? I can try to divide everything for the denominator. I can factor out this 1 minus I, then 1 minus z minus I over 1 minus I. Right? Then this is, I can safe to say that this is, n from 0 to infinity, and z minus I by 1 minus I, everything to the end. Okay, so and let me try to check the radius of convergence. And so this power series expansion is true if and only if this number, this common ratio. So this number, I really want to say call this guy as a common ratio of the geometric series. And this number the absolute value of this number should be less than 1, right? So to check the radius of convergence, so I require that this number, and it turns out this number, this is the magnitude of the denominator, which is just square root of 2, and we require that this number to be less than 1. So so just as we expected, so our radius of convergence should be exactly square root of 2. Okay, all right. So this is about the Taylor series. So okay, so let me just one last time. So let me go back to this Taylor series. So according to this according to the theorem, the Taylor series is a power series, right? So this is very special case of power series. But I can say the opposite. So what does it mean? So suppose that you have a power series that has some non-trivial radius of convergence. So in that case, your power series should be converging to some analytic function on inside of the circle of convergence, right? And what I will claim is that the function that is represented by that power series also must have some Taylor series. Why? Because your function is also analytic, right? Because, remember, if any function defined by using power series is automatically analytic. So this is what we proved in my last lecture. And what I will say is that the function represented by power series should have a Taylor series expansion, and that Taylor series should be identical to its own power series. So, which is the converse of this? Which is I say this is somehow converse of this statement. All right. So let me try to give you the statement. Power series of a non-zero radius of convergence. Is the Taylor series of is some. Okay. All right. Okay. So I also want to prove this. Okay. So this is what I want to prove. I have a power series, which I call f of z, and this guy has some non-zero radius of convergence. And so f of z is obviously defined by using power series. And something we know, what we know about this function is this function is analytic on this domain. Okay, now what I want to do is this number. So in order to prove the claim, that what I want to prove is that this number, this coefficient, is precisely the nth derivative of function f evaluated at the center and divided by n factorial. If I can prove that, then well, the claim is then my proof is done. Okay, so how do I prove this? Please allow me to take advantage of the theorem that we used in my previous lecture. I hope you remember this. Suppose, well, last time we had this theorem. For any curve, a curve in the circle of convergence, and G is any continuous function on this curve. Then what we had was, if you integrate the G times any analytic function, so G times this power series, not any analytic function. So well, the precise statement was G times of the function defined by using the power series is the same as z minus z0 and to the nth and dz. Yeah, that was the statement. Yeah, do you remember this? Yeah. Okay, so by choosing a clever choice of function g of z, then I may be able to prove that f(an) is actually the coefficient given by using the Taylor series. Okay, so in this case, I will choose that my function g to be just 1 over 2 pi times I, and z minus z0, and so I have used index m, so m, I will say just m plus 1. Here, m is a number from 1, 0 to dot, dot. Is it continuous on this circle? Yeah. This is obviously continuous on this circle of convergence. As long as no. Oh yeah, sorry. I should put just one more additional assumption for this curve. Okay, and also we let C to be a circle of radius R0. Yeah, I want this radius to be less than R, and center is Z0. Okay. Okay, yeah. By doing so, now I am pretty sure that this function is everywhere continuous on this curve thing, right? Okay. Okay. So, okay. Now, just what I want to do is just take advantage of this theorem. All right. So, for the left-hand side, g of z, f of z, dz. This is just 1 over 2 pi I c and fz dz, and z minus z0 and m plus 1. We know this very well because of the extension of the Cauchy's integral formula. So it turns out this is m factorial, and f m's derivative evaluated at the center of the power series. Okay, well, for the right-hand side, which is from n0 to infinity, an times 2 pi I which is, well, I have z minus z0 and m minus n and plus 1, right? Because this is on the top and this is on the bottom. Yeah, good. And dz. Okay. Okay, so what I need to do is I want to compute this line integral. But this is something that we did a long time ago. Yeah, I hope you remember. I hope you all remember this. But this integral. So in particular, if this is your integrand, then almost always the integral of this guy equals to 0. What? Well, as long as this integrand is not equal to 1, as long as this exponent is not equal to 1, then your function has the antiderivative, right, on this endless domain. Therefore, NC is a obviously closed curve. Therefore, the answer should be 0. But there is only one exception. What was that? So if this exponent equals to 1, then whose antiderivative should be the logarithm function. But the logarithm function is not well defined on this annular domain. So you should get some non-trivial number out of here, right? So, and so for this guy, is 1. Well, so this guy is 1 if m minus n plus 1 is 1, and otherwise 0. Yeah, I actually don't like this statement that much. So let me simplify this a little. So I can cancel these two ones from left and right. So, oh, sorry. Yeah, I messed up. And okay, great. So very happy thing happens. For this summation. Well, this guy, almost every guy next to this summation equals to 0, but there's only one exception. So the only one guy survives out of this summation, which is AM, right? Okay, so now compare the left-hand side and right-hand side, and we know those two guys are the same thing. And so AM equals to AM is precisely the coefficient that was expected from the Taylor theorem. So every power series is the Taylor series of its own function. its own sum. Great. Before I end this section, so just please allow me to give just a little bit redundant remark on the operations of the power series. So do you remember this well? So when we are also, I keep mentioning the freshman calculus, but so they're really related to each other. So suppose that you have two different power series and their centers of expansions are the same thing. In that case, you can add them and you can subtract them or multiply them, or you can even divide them, right? And well, the addition, subtraction, and multiplication, division is they are all going to give you the power series of sum, subtraction, multiplication, divisions of these functions. That is being represented. So I mean, in other words, you can actually do the term by term addition, term by term multiplication, and term by term division. Well, not term by term division. So I should say the long division. But I mean, by applying the exactly same trick that was used for that was used in the operations of the polynomials, then you can find the power series or the Taylor series of the functions that is being represented. So that is something that I want to emphasize. The multiplication of power series. Well, in general, so I want to say some operations between the power series. Well, I have two functions. And they have the same center of expansions. This is my f, and this is my g. Then, well, sorry. So I also should not forget about the radius of convergences. This is R1, and this is R2. Oh, sorry. Then fz plus minus gz. What is the power series of this function? So this is, well, obviously an plus minus bn and z minus. The addition or subtractions of these two power series has a coefficient that looks like this. How do I prove this? Well, this is not a big deal because, well, we are talking about the summation and we're talking about the summation of the infinite series, and the convergence of the infinite series is well defined by the partial sum sequences. And well, you can always put to add or subtract two partial sum sequences. And if those two guys is converging to some number, and the addition and subtraction of these two power series also should be converging to some number, which is guaranteed, which is also guaranteed. So well, there's nothing much to prove about this. So let's take this for granted. What about the multiplication? Oh, sorry. Yeah, I keep forgetting about the radius of convergence. And for this guy, well, of course, since I cannot say anything about beyond the radius of convergence, so the radius of convergence of this resulting function should be the minimum between R1 and R2. And I want to talk about the multiplication. Well, so if you multiply these two functions, then product of two analytic function is also analytic. Therefore, f times g also must have some power series expansion, Taylor series expansions at the center equals to z0. And in this case, the coefficient, the Cn, must be Cn is from k0 to n, a k times b n minus k. Okay. So in other words, the power series, the Taylor series of product of two functions is also very easy. Because, well, how do you get such coefficient Cn? Well, you multiply two infinite degree polynomials and you write them in descending order, and you're gonna get these coefficients. So that is the point. Well, proof is somehow very tedious, so please, I'll be quick. Okay, so all right. So this is the Taylor series of this guy. And all I need to check is, so this is the Taylor series of this guy. So therefore, the Cn must be the f times g nth derivative evaluated at there at the center and divided by n factorial, right? So if you can check, if you can prove that this is true, then yeah, so this one has to be true. And I want to show that I want to claim that this guy is precisely this one. Okay. So we want to show okay. Yeah, this is very tedious exercise. All right, so to show this, well, inevitably, I will need to take the nth derivative of f times g. So how do you get the nth derivative of the f times g? Yeah, obviously by using the product rule for the differentiation. So f times g, the first derivative is f prime g plus f times g prime, and f times g second derivative is f double prime plus 2 times f prime times g prime, and f g double prime. And if you keep writing these derivatives on and on, then I guess you can easily figure out the patterns lying underneath. Taking the nth derivative, this is going to be from k0 to n, and choose k, and f k's derivative times g, sorry, n minus k's derivative. Yeah. Well, how do I know that? Yeah, you can easily find out using the mathematical induction. Yeah, which is not interesting. So yeah, and I guess we are done. So fg and g0. This is, this is a binomial coefficient. So please allow me to write down, rephrase this guy by n factorial over k factorial times n minus k factorial, and fk to the of z0 and g n minus k and g0. And this guy is, well, this is just k times ak, and this is what? This is n minus k factorial times b n minus k. And you're simplifying them together, and so, well, and this number, these two numbers, they got canceled by this denominator, and eventually this n factorial, this is nothing to do with the index k, so this guy can be taken out of this summation. Then your proof is, then I guess you can easily claim this. You can easily show that this is true. All right. Well, so this is the trick that we proved that this is how we found the coefficient of this product of two functions. Well, likewise, you can use exactly the same trick for the division of two analytic functions. Suppose you have two functions and you have two analytic functions and you take the quotient of these two functions. And for the domain that the denominator is not equal to 0, then you know your function is also analytic. Your quotient function is also analytic. So that means you can naturally expect the Taylor series of this quotient function. Then how do you know that denominators of this quotient function? Well, I can use the same. Well, you can prove that exactly the same way, but that will be too much tedious. But with the point is these coefficients can be obtained by applying the former long division algorithm onto two infinite degree polynomials. And once you do that and you write down the nth result in descending order, then you know your coefficient. Yeah. So yeah. Well, for those of you who already checked the homework exercises that I uploaded a couple of hours ago in PRMS, yeah, there is some exercises regarding this long division algorithm. Yeah, that won't be that present to solve. But anyway, once in your lifetime, yeah, maybe you can try to do that on your own. Maybe, yeah, just one time in your lesson. One last time. Okay. Now we are turning to the next section. Now we want to talk about the Laurent series and the residue integration. Okay. Well, so what was the Taylor series or the power series? The power series was the way that we used to represent any given analytic function in terms of the polynomials, right? And especially the choice of the center is considered very crucial. And well, in this problem, so if your choice of your center is away from the singularity of your function, sometimes your function may have some singularity. But if your choice of center is not away from the singularity, then you can get a circle radius. And the circle radius, this is an open disk, which is clearly simply connected. But however, from time to time, it is required to have your Taylor series. It is required to have a power series expansion, not on this analytic point, but sometimes from time to time, you may want to have your power series representation of function centered at the singular point. Why? Why is that necessary? Well, because we are living happily in this world of analytic functions, but sometimes we need to classify the singularities. Well, in complex analysis, well, later on we're going to talk about the singular point, but singular points are not the same. So there are many different types of singularities. Well, and the analysis of the singular point is, I guess, the most important part in the mathematics and engineering, right? Because, well, if you're engineers, then, well, if you're working on some smooth functions, then where is fun inside? Well, sometimes you can find a singularity, and if you can find out what happens in what happens in the neighborhood of the singularity, then you can also derive many interesting theorems out of it. So sometimes it is necessary to have your power series centered at the singular point, and in that case, your series cannot be called a power series anymore, because well, your summand may consist of some rational functions, not just polynomials. So things are getting interesting and more interesting. And in order to do that, So first, we want to talk about the series representations, not on simply connected domain, but some non-simply connected domain. Okay, more precisely, I want to find some series representation on analogous domain. So this, well, in order to do that, we want to discuss about the Lorentz series. Yeah. So I will first try to give you the statement of the Lorentz series. This is quite long, so yeah. I have a function which is analytic. F is analytic on annular domain. You know what I mean by annular. So annular domain is well, topologically speaking, so annular domain means a disk with a puncture inside, hole inside. So this is what I mean by annular domain. But we are not talking about just any regular annular domain, but we'll be talking about this very specific annular domain. So like this. So we are talking about this. So this is the point Z0, and this is the inner circle, and this is the outer circle. And the distance from here to there, this is R1, right? Yeah, and this here to there, this is R2. And we are assuming that our function is analytic. So I have no idea what happens inside of this inner circle, but what we know is my function is analytic on this analyst. Okay. And this is centered at Z0. And let's see, denote any positively oriented simple closed curve lying in that analysis. So, well, that means I have some mysterious curve which is simply closed and positively oriented. So this is my curve C. Okay. Sorry. All right. And the conclusion is, the claim is, for every point in that annular domain, now I have a series representation of the function f. So I have, well, so from now on, so I may not be able to call this guy as a power series, right? Because in order to be power series, then the exponent must be always non-negative. But clearly here, the exponent is here, there is, I have one additional term over there. and whose exponent is clearly negative, right? So from now on, this guy cannot be called a power series anymore. So this guy has a name. So this guy is called the Lorentz series. And also, on top of that, so these coefficients A and Bn can be computed by and well, it is indices are from 0 to 1. And this index Bn is also 2 pi I z minus z0 minus n plus 1. So these are well, so An represents An means the coefficient associated to positive exponent, and Bn should be understood as the coefficient associated to negative exponent. Yeah, and well, these numbers, these coefficients A and Bn, they look almost identical. The only difference is these exponent. This is positive and this is negative. So in some other textbook, so they sometimes write sometimes we write so the index, index is running from minus infinity to plus infinity, and Cn z minus to the n, where Cn is 1 over 2 pi times I, the integral over f dz z minus z0 n plus 1. Yeah. At this time around, this integer, this number n should be some negative integer. Okay. So this is the Lorentz series. Okay. So my today's last objective for today's lecture is to prove the theorem. So let me try to prove this. Well, just like my previous lecture, so without losing too much generality, so I am assuming the center of this Lorentz series is the origin. Well, if you can prove when the case when z0 equals to 0, then later you're always free to parallel translate this formula by some number, then you can get this general form. Okay, so yeah, I really want to draw the picture of this. This is a complex plane, and this is the center. I have this is the inner circle, and this is outer circle. Oh, sorry. Yeah, I want my circle to be somehow bigger than this. This is the outer circle. And now choose any point. The analysis. So, well, I have chosen this guy. This is my Z. And So, and please allow me to say the length, the distance from the origin to this point is r. This is r. Okay. Now, other than this, I want to choose two other circles. Now choose two circles of radius r1 and r2 such that r1 is less than r and r2 is greater than r. And we say they are both positively oriented. And obviously center. So, well, so this is, well, first circle, and this is the second circle. Okay, and well, we are assuming these two guys are both positively oriented. Okay. Yeah, for this inner circle, I'll say this is C1, and this outer circle, I will say this is C2. So C1 is R1, and C2 is Z is R2. Okay. Other than that, yeah, allow me to choose just one last circle. And this guy, this time, this is very small one. Well, which lies between the area bounded by the circle C1 and C2. And this last one, this is also positively oriented. And this guy is encircling this point of interest Z, right over here. So choose a small circle, which I will say the last one is gamma. And this is centered at the point Z, and this last circle is contained in a closed annulus. Okay. All right, and this is positively oriented. Lots of conditions. Okay, so yeah, now I have very interesting, very ugly picture going on here, and I want to focus on the region. Yeah, so well, I am trying my best to give you the beautiful illustration of what is going on, but yeah. So this is, well, I want to just focus on this yellow shaded region, and well, because of this assumption, F is assumed to be analytic on this annular domain. Therefore, F must be also analytic at every point in this shaded region. So therefore, I am safe to apply the Cauchy-Gorsa theorem. So do you remember that? Cauchy-Gorsa theorem on the multiply connected domain. So in this case, so the integral of C2, which is the greatest one of, okay, so Fz, sorry, yeah, I changed my mind. Fs ds and S minus Z minus C1, which is the inner circle right over here, and Fs ds S minus Z, and minus, lastly, the integral over gamma And well, if you look at this integrand function, f of s divided by s minus z, and the singularity of this function only happens at this point. But clearly, this point is out of consideration from this, from the perspective of the yellow shaded region. So therefore, this whole integral must be 0. This is a Cauchy-Borset theorem. Right? Oh, because, well, for the multiply connected domain, you have function f, which is analytical here. And if this is the C1 and C2, then we know that C1 so this was the path deformation of path principle, right? So if you remember this deformation of path principle, then I'm using exactly the same trick, but with just one additional port over this. Okay, all right. Many interesting thing is going on here. Yeah, so I have 3 different terms appearing in this equation, and I feel like this guy is the easiest. Because the Cauchy's integral formula, I know that this guy is 2 pi I times f of z. Okay, so f of z is 1 over 2 pi I which is C2 f s ds by s minus z again minus 2 pi I times like this. All right, yeah, okay, good. Oh, please allow me to change the sign. So I want to change the sign of this guy to be positive, but I cannot get this sign for free. So okay, all right, okay, good. Now, I want to use the same trick that I used when I was trying to prove the Taylor's theorem. I have s minus, well, inside of this integrand, I have this guy over here, and this is yes. Well, last time we said this is s z over s, and this is just 1 over s, just carries over, and raised by power of n, and this is not good. So okay, so well, to get the zn and s minus z times sn. Right? Do you remember this? Or if you're not very much, if you're not too much comfortable with this expression, then well, this is the finite sum of the geometric sum, right? Geometric series. And this is so this is going to be what? This is going to be what? Just 1 over and 1 over z minus and everything to the n's. Okay, and I want this guy to be so okay. So so this is this, and if I add this guy by that, then I'll probably I will get this. Yeah, this is just high school level algebra, so not too much complicated. Okay. Okay. So from n0 to n minus 1, and I have as n plus 1 times z to the n, and plus z to the large n carries over, and oh, sorry, yeah, I know I just made mistake. Yeah, sorry, this is not right. Good, yeah, good. Okay, and multiplying by this guy with this factor over s minus z. Now it's now restored. Yeah. Okay, great. Yeah. I'm having not good. So I have some trouble working on the high school level algebra. Yeah, but I guess this is right. Okay. So this is about it. This guy is some ugly expression, but still equivalent to this guy, this one. And I want to have the same expression for this one. But the only difference is, but I guess I can easily get the expression. But what I need to do is just exchange the row of the s and z. So z minus s is now every s should be now z. Oh, no. So this is Sn Zn plus 1 plus Sn Z minus S and Zn, right? Okay, but okay, but for future purpose, yeah, I should say that this is oh, sorry, yeah, right. Yeah, I should be changing the indices. So this is, if I change this guy to be, then this is Zn times Sn plus 1, right? And this one just carries over. And okay, just one last time. So S minus N plus 1. And okay, good. All right. Okay, so I have this and that. Okay, so now things are getting really confusing. F of z is 2 pi I times C2, and well, here I am multiplying f of s over here. So I can just copy and paste this guy. And multiply by f of s. And same thing is true for this one. And plus another integral Okay. Good. Then from n0 to n minus 1, I have 2 pi I of C2. Since this is a finite sum, yeah, I can, and ds and everything times Zn plus Zn 2 pi I times C2 Fs ds S minus Z and Sn. Okay, and I have this one and plus from n to n 2 pi times I C1 Fs S minus n and ds 1 over Zn plus 2 pi I times Z, and well, since Z is nothing to do with the variable S, so and C1 Fs Sn over Z minus S everything ds. Okay, great. Okay, so we are almost done. So let me compare this expression and that expression, which is exactly same as this and that, right? So this is AN, this is BN. So all I need to do is to show that these two guys tends to 0 as n goes to infinity. So for simplicity, I am saying this guy to be, and this is, I'm going to call this guy sigma n of Z. So it suffices to show that these two guys, they both goes to 0 as n goes to infinity. Yeah. First, I always show that this guy should be tending to 0. Well, this is I say this m is the maximum value of modulus of f of s on C1 and C2. So, well, yeah, clearly there must be some such a number. And using the ML inequality, okay, so, well, the magnitude of these two guys is, well, what is my Z? Well, here, yeah, going back to here, the magnitude of Z was assumed to be R. So this number is bounded by Rn, and the 2 pi I is now 2 pi because we are talking about the modulus, and times the maximum value of f of s was m, and well, the absolute value of f of z. So, but I should be also saying that this guy is bounded below by s minus z. Here, but we are talking, well, this integration is happening on the C2, and C2 is a circle with radius R2, right? So, okay, sorry, yeah. So, well, so this one must be R2, and R is just R, right? Okay, so this is also bounded below by, so bounded above by, so R2 minus R1, that's just R, and times, lastly, the length of the curve that is being integrated. So this is a circle of radius R2, right? So 2 times pi times R2. Okay. Okay, all right. So these two guys, they both cancel. So I have R. Oh, something is missing here. Oh, sorry. I just messed up this. So this is S. So and this is S is since this S means so we'll point on the circle of radius R2. So this is R2. Okay. So this is, well, I have R over R2 and everything raised the power of N and M and R2 minus R. And am I good? Yeah. So, okay, good. And well, since we're comparing R and R2, well, obviously R2 is bigger than R. So therefore, this is less than 1. So this guy is tending to 0 as n goes to 0, as n goes to infinity. What about sigma n of z? So same trick is also true. Well, so this is this guy here. But what I have here is 2 pi times z. So this is r to the n. And this is the, well, by ML inequality. So this is maximum modulus of f of s. And this time around, since this integration is happening on the circle C1, and this circle C1 has the radius R1. So this is R1 to the n. And by the same reason, this denominator is bounded by this guy and times the length of the curve, which is R1, 2 pi times R1. So eventually, I have R1 over R, everything raised to the power of n, and m times R1 by R minus. Yeah, sorry, I just missed R2 here. Yeah. Okay, so again, well, comparing R1 and R2, this time now R is greater than R1, so this guy also should be tending to 0 as n goes to infinity. Okay, great. So we actually have almost the same formula that I have promised in the statement of the Lorentz series. Oh, no, sorry. My proof is not quite done here because, well, in this statement, my curve C, this C is just not a, this is curve is C1 and C2. So these two guys are very rigid circle. This is very specifically, this is very concrete and circle. This is clearly a circle that centered at the 0 and whose radius are R1 and R2. But there is no such condition imposed on this theorem, right? Because, well, so this is just C. This C can be any curve that is enclosed in your analysis. So, but proving this theorem should be not terribly complicated because, well, your function is analytic on this analysis domain. And in that case, because of the path deformation principle, you can always replace your circle to be any simply closed curve with positive orientation. So, well, therefore, C1 and C2 can be replaced by this any curve with positive orientation encircling your annulus. So therefore, the Lorentz series has been proved. Okay. All right. Well, I have 5 more minutes, so please let me try just one more exercise. I have a function sorry, 1 z 1 plus z. I want to find the Lorentz series of this guy. In the punctured open disk. Just one more remark on the two radiuses. This is the, I said this is the inner circle and this is outer circle. But this number can be 0. If this number is chosen to be 0, that means you can actually, that means your function is almost analytic in the disk of radius R2, but your function fails to be analytic at the precise center. That means your function has the one singular singularity at this point, right? If you set your z R1 equals to 0. Likewise, this number R2, well, obviously R2 should be a number greater than R1, and you can also say this guy is equals to positive infinity. In that case, well, your analytic domain consists of entire complex plane minus the origin, minus the center. Okay, so, well, coming back to this exercise, I am supposed to find the Lorentz series of this function, this guy. Instead of just directly applying the formula that is given in the theorem, so practically most times we just make use of some algebras. We know how to find the series representation of this guy, right? 1 over z, 1 over 1 plus z. And if you just multiply 1 over z to that power series, then you're going to get the Lorentz series. So just like this. Sorry. I was not good at copying and paste of this question. So. Well, do you know how to get the power series of this? Yeah, this one you can easily get this guy without too much trouble. So this is -1 and z2n from n0 to infinity. So this is the power series of this function, right? Now, what I want to do is I multiply 1 over z for everything, then -1. Okay, now since my function 1 over z is not defined at the center of this expansion, so now this domain is now my puncture. This is the punctual domain, and well, for the least index n equals to 0, then this exponent is not positive anymore. So your exponent here is the negative exponent. So that means this is when n equals to 1 to infinity. So this is, I say this is the Lorentz series of a function. So this is the part where the positive exponent happens, and this is the part where the negative exponent happens. Well, so most times, especially, so typically, if your function of interest is a rational function, rational complex function, then your negative exponent part usually does not go to infinity. So it somehow, almost always, it somehow ends at some finite. And there's some finite terms. Well, sometimes you can find the example, so that has infinite remaining negative exponent terms, but we're going to talk about that later. However, for rational functions, this is very typical form of the Lorentz series. Okay, so I guess this is for today, and see you next time. 예.
영어를 배우고 보다들 혹시 중요한 것이 마지막에 말씀하신 질문 불안정하다고 표현해요.
왜 아까 왜 그러냐면요. 그러니까 AN이 아까 제가 한 거는 이제 AN이 10파이에 C1에 어쩌고저쩌고 있고 BN이 10파이에 C2가 어쩌고저쩌고 이렇게 있고. 그렇죠. 그렇죠. 그러니까 지금 이게 뭐냐면은 그러니까 이 얘기인즉슨 제가 한 증명은 그러니까 이게 요 애널라 도메인에서 사실 이게 근데 우리 원래 스테이트먼트는 이게 없거든요. 그냥 아무 C나 하면 된다고 아무 C에 대해서나 그러니까 파지티브 오리엔테이션 가지고 있고 한 바퀴를 돌리는 아무 C에 대해서나 하면은 된다라고 나와 있는데 제 증명은 이렇게 생긴 아주 특별한 모양의 C1 시트에 대해서만 된다고 나와 있어요. 증명한 거잖아요. 그렇죠? 그렇지만 그걸 우리가 이거 C1 시트를 그냥 C로 바꿔도 큰 문제 없다.
근데 C1, C2를 어디 있으면 애초에 다른 서버에서 인테그럴하는 거 아니에요? C는 하나의 커브인데
네.
C와 C2랑 되게 다른.
그렇죠. 다른 커브죠. 그런데 지금 여기 보시면은 이게 뭐였지? 이게 보면은 2파이에 fs ds s 마이너스 s g0에 n 플러스 1 그렇죠? 그렇죠?
네.
그러니까 요게 근데 요 함수 자체는 요 애널러스 안에서 언제나 애널리틱 하잖아요. 그렇죠?
네.
그렇죠? 언제나 그러니까 함수 안에서 애널리틱 하기 때문에 이 경우 약간 또 패스트 데포메이션 프린서플 기억나시죠?
네.
그렇죠? 패스트 데포메이션 프린서플에 의하면은 여기 얘가 애널러스를 한 바퀴 도는 이상 C1으로 하든지 C2 하든지 뭐 C100으로 하든지 어떤 건 상관없다는 거죠. 그렇죠? 그렇죠? 그러니까 얘들 그래서 그걸로 그 원리 때문에 별거 아니에요.
이미 커브 C가 무조건 근데 이렇게 한 바퀴 감싸는.
네. 근데 우리 커브 C1과 C2는 이미 한 바퀴를 감싸고 있기 때문에 얘를 한 바퀴 감싸서 다른 어떤 친구로 바꿔도 큰 문제 없다. 사실 요거를 다시 쓰고 있고 사실 이거 또 쓰고 있고. 네. 네.
저원 벡터하고
네.
저희가 그 프로그램 중에서 Z1에서 컨버지 하면은
네.
Z0랑 그 원을 어떻게 이렇게 하는 원을
네.
디스크 내에서는 컨버지하고
네.
컨버지하는 거 배웠잖아요.
네.
근데 여기서 또 띄우려 보면은 여기서도 그 Z0에서
네.
디스크 R을 반지름이 아닌 디스크 내에서
네.
컨버지 하면은 그 디스크 내에 어떤 Z1을 잡아서
네.
그거를 가지고 만든 디스크 내에서는 유니폼을 컨버지 하다고 했죠.
네.
근데 뭔가 이거 두 개가 뭔가
이거 이해했어. 그러니까 뭐냐면요. 그러니까 여기서는 그러니까 뭐냐면은 요 안에서는 그러니까 absolutely convergent 하는 거죠. 그렇죠?
네.
그렇죠? 근데 그러니까 요 absolutely convergent 하는 건 뭐냐면은 이제 AN 그렇죠? 요게 수렴한다는 소리잖아요. 그렇지?
네.
그렇죠? 그런데 이건 뭐냐면은 한 점에서 absolutely convergent하게 확인이 되면은 그럼 요 디스크 안에서는 그러니까 요거 있죠. SN이라는 친구. 그러니까 1부터 0부터 n-1까지 A, N, G-. 요 디스크자 D라고 할게요.
네.
이 녀석은 D라는 도메인에서 그냥 폴리노미얼 함수라고 생각할 수 있잖아요.
네.
그럼 요 녀석들은 이 녀석으로 그러니까 S. 이 녀석으로 유니폼 하겠습니다.
네.
그러니까 absolutely convergence와 uniform convergence가 약간 헷갈리시나요? 아니 그런 아닌가?
그러니까 근데 absolutely convergence 하면은
네.
convergence 하잖아요.
네, 그렇죠.
근데 그 유니폼리 컨버전스라는 거는 이 도메인 내에서 어떤 포인트에서든 컨버지 한다는 거잖아요.
아니 유니폼리 컨버전트 하는 건 뭐냐면은 그러니까 어떤 함수열이 SNG가 SG로 유니폼리 컨버전트 하는 건 뭐냐면은 어, 모든 엡실론에 대해서 우리가 어떤 n을 찾을 수가 있어가지고 n은 엡실론만 유도하는 값이에요. 그래서 인덱스가 n 엡실론보다 커지면은 SNG와 SG의 차이가 엡실론보다 달라진다는 거죠. 그렇죠? 그러니까
네.
여기서는 이게 중요한 게 엡실론이 여기 G의 위치에 인디펜던트하게 우리가 잡을 수 있는 그러니까 G가 이 도메인 D 안에만 있다면은 그 도메인 D 안에 어떤 G가 와도 써먹을 수 있는 N 엡실론을 찾을 수가 있다는 거죠. 그렇지?
네.
근데 근데 이 앱솔루트리 컨버전스는 뭐냐면은 이 친구는 사실 뭐 그렇죠? 앱솔루트 컨버전트 하는 건 뭐냐면은 요 특별한 G에 대해서 요거는 요거 그러니까 이거는 이게 뭐 S로 수렴한다면은 이제 이게 있는데 이 녀석이 이 초이스 오브 엡실론이 G에도 의존을 할 수도 있다는 거죠. 그 차이인 거예요.
어,
왜?
네.
네, 제가 먼저 먼저 얘기하세요. 제가 대답을 제대로 하고 있는 거예요.
네. 두 개 개념 차이는 뭔가
네.
이제 알겠는데, 그니까 이 조건이
네.
뭔가 저는 똑같이 느껴져가지고, 그러니까 왜냐면 여기서도 어떤
예, 맞아요. 네, 일단 말씀하세요. 네.
그래서 이 두 조건이 저는 똑같이 느껴져서 그러면은 이 앱솔루트 컨버지랑 이 유니폼 컨버지랑 이 띠어럼에 따르면 같게 적용되는 거 아니에요?
그쵸. 그렇게 생각할 수도 있어요. 그런데 유니폼 컨버전스는 사실 함수 공간에 있는 시퀀스가 수렴한다는 거라고 생각하시면 되고요. 앱솔루트리 컨버전스는 그냥
네.
G라는 포인트가 결정됐을 때 그러니까 포인트 와이즈리 컨버전스 하다라고 생각하셔야 돼요. 네. 그 차이.
그냥 관점의 차이라고
예.
하고.
예, 그래요. 네. 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 로렌스 시리즈가 뭐냐면은 그러니까 이제 그러니까 애널러스 도메인 위에서 애널리틱한 함수가 있을 때 그 애널러스 도메인 위에서의 그 함수의 시리즈 레프레젠테이션이라고 보시면 돼요. 그러니까 우리가 어떤 함수가 있으니까 요 안에서는 무슨 일이 일어나는지 모르겠어. 근데 여기서는 어네저틱 하대. 그러면은 요 안에서 함수를 어떤 애널리틱 함수 F가 있는데 이걸 이 안에서 뭘 계산하고 싶어. 그럼 우리가 어떻게 할 수 있냐면은 첫 번째 그냥 여기 애널리틱한 점에서 센터를 잡고 시리즈 레프레젠테이션이 있어야지 계산할 수가 있잖아요. 그렇죠? 일반적으로. 그렇죠? 그러니까 여기 이 점을 중심으로 잡고 거기 이 정도 레이디어스 오브 컨버전스에서 우리가 요거를 이 함수 f의 시리즈 레퍼런트를 잡아서 이 함수 요 근처에서 계산할 수도 있겠죠. 그렇죠? 그런데 나는 이렇게 하고 싶지 않단 말이야. 물론 이렇게만 해도 충분히 만족한 사람이 있겠지만 나는 요 점 어딘가에서 중심을 잡고 있는 레프레젠테이션을 계산하죠. 그러니까 이 애널러스 도메인 전체를 커버하는 어떤 레프레젠테이션을 잡고 싶어. 아까는 요 영역밖에 커버 못해. 그렇죠? 그렇게 하기 위해서는 어 요게 필요하다. 그러니까 만약 그래서 요 전체 영역을 다 커버하는 시리즈 레프레젠테이션을 가지고 싶으면은 어떻게 되냐? 그럼 필연적으로 이때는 더 이상 이제 파워 시리즈라고 부를 수는 없겠죠, 이거는. 그렇죠? 파워 시리즈는 포지티브 엑스포넌트를 가지고 있는 친구들만 파워 시리즈죠.
네.
근데 이거는 네거티브 엑스포넌트 가지고 있기 때문에. 근데 이 친구도 보면은 요 G0가 요 안에 있는 점이잖아, 그치? G0가 그러니까 여기에서는 이 레프레젠테이션이 문제가 생기겠지만 우리가 궁금한 건 요 애널러 도메인 안에서의 레프레젠테이션이죠, 그치? 애널러 도메인 위에서는 이 G가 절대로 이 싱귤레이트를 찍을 위험이 없겠지. 그렇죠? 그러면은 그때는 그래서 요 익스프레션 자체는 요 애널러 도메인 위에서 완전하게 밸리드한 익스프레션. 그렇죠?
네.
그리고 요거는 어차피 우리가 결국 실제로 계산할 때는 뭔가 파이나이트한 텀 안에서 뭐 거기 트렁케이션 시켜야 될 거 아니에요. 이렇게 이런 식으로. 그렇죠? 요것만 하면 요거 자체는 우리가 더하기 빼기 곱하기 나누기 모두 계산할 수 있죠. 그렇죠? 그래서 그러니까 이거 자 그래서 아까 요거랑 비교해 보면은 요 익스프레션은 훨씬 더 넓은 영역을 한꺼번에 커버할 수 있는 익스프레션. 그리고 지금까지 우리 파워 시리즈 레프레젠테이션은 우리가 심플리 커넥티드 디스크로 생긴 도메인만 우리가에 대해서 적용할 수 있었죠. 근데 이거는 심플리 커넥티드 되지 않은 도메인에 대해서도 사용했어요.
그럼 그 상황에서만 사용할 수 있다는 이런 홀이 있을 때도.
홀이 있어서 만약에 이게 만약 안에 전체가 어나리틱하다 그럼 이 부분에서 나중에 보면 사라지겠죠. 아까 요거였잖아요. 이게 BN이
홀이 있을 때 사용하는 테일러 시리즈 정도를 이해하는.
네 맞아요. 홀이 있을 때 사용한테.
알겠습니다.
네.